With the grain simulations that we've run so far, all of the grains are activating all at once, but for a disintegration effect, we typically want this disintegration to propagate all across the surface in an interesting and organic way. So we can use a growth or infection solver to animate this progression across the surface. And to animate this with a growth solver, I'm going to start by just making all of the grains black, and we're going to animate some color across this. So just drop in a color sop, and I'll set the HSV V value to 0 to make these black, and let's bring back our light viewport just to make this a little bit more visible. And now we're going to define some starting points for the infection to begin at. So I'm just going to, once again, use a noisy sphere to group some of these points. So let's drop in a group, and I'm going to call this initial infection. When grouping by geometry, the group type has to be points. Let's turn off the base group, turn on bounding regions, and select bounding object, and then connect our black grain points to the first input and the grouping sphere into the second. And it looks like my transform here is broken, so let me just grab my creature scale once again, since I had originally set up these sphere positions based on the non-scaled version of that creature. Okay, there we go. So we just have a noisy sphere that's grouping these points at the tips of the tail here. And then we're going to propagate this color starting at these selected points here. So let's use an attribute adjust vector to make those grouped points pure red. So the attribute name on this adjust vector will be CD. And then for the adjust value, we can set it to add constant and give this a red color and display that. And right now it's making all of the grain points red because we haven't selected our group. So then back up at the top, the group parameter, let's select initial infection, which is not showing up in our drop down here, so we may need to just type that in. You can see this initial infection group does exist, so let's try typing it since it's not offering it in the drop down there. Okay, typing in that group manually gives us the selected points getting turned red, and now we can delete that initial infection group because we don't need it anymore. So I'll drop in a group delete and select that initial infection. And now I'm going to use some noise to vary the speed at which this infection grows across the surface. It can be fine to use a constant speed across the surface, but oftentimes anything we can break up with some noise should create some more interesting behavior. So I'm going to drop in an attribute noise, connect that after our group delete, and we'll set this to be a float instead of a vector. And this attribute name is going to be called grow speed. And as you saw before with our attraction weight up here, I'm going to use a color sop to visualize this attribute. You can use the viewport display visualizers, but I still like using color sops even if it's a little bit more old school. So I'm copying the view attraction weight, and this one I'll call view grow speed. And we'll change the attribute name inside the color sop to grow speed and display that. And it looks like this is kind of a small scale noise. I want something maybe a bit larger scale so that we have some more obvious patches of smaller or faster propagation across the surface here. So on the attribute noise, let's increase the element size. And we can also vary this differently on different axes as well. So perhaps if we wanted to stretch out these noise shapes on the x-axis, you can click the X, Y, Z button here and scale it differently on each individual axis. And it looks like our current noise values are in a fairly limited range here, so I'm going to turn off this output raw value so that we get a more pure black and white range on our output noise values here. and this is looking pretty good. These nice kind of stripy patches of black and white values for that grow speed should hopefully give us some nice variation where this infection will propagate a bit faster on the brighter sections there. And now would be a good time for us to import the animated creature that we want to disintegrate so that we can start deciding on the timing for this disintegration. So let's drop in an object merge, and I'm going to point this to object creature flying basic, and let's see if out squid 1 is the correct one that we want to disintegrate. I'm going to go back to my render wide camera here, and perhaps bring back my other objects in the scene visible for reference here. Okay, so yes, this is the creature that I want to disintegrate, and I'd like to see it flying around for a little bit before we actually start the disintegration. So in this case, I think it would be pretty cool to start disintegrating it when it's approaching the center of frame here. So in this case, we'll say that's about frame 95. So we can start accumulating this infection growth with a solver that begins at frame 95. Now, we've taken a look at DOPNets to do proper simulations where it takes the result of one frame and processes it with a certain set of simulation parameters to get the next frame. But we also have what I guess is kind of a different type of simulation. It's not really a dynamic simulation in the way that we think about particles or grains or rigid bodies or pyro or something. But if you just create a solver and the SOP context, this gives us kind of a simulation that allows us to just define very customized behavior from one frame to the next. So if you dive inside this SOP solver here, you can see that this gives us access to the inputs coming into that SOP solver, and it also gives us access to the previous frame's output. So to propagate this infection color across the grain points, we're going to compare each frame to the red portions on the previous frame and check the proximity between them. So let's use a distance from geometry, and we'll take the first input of our SOP solver here, and let's once again zoom in on this here, and we're going to put that into the first input of our distance from geometry. And then the second input for distance from geometry will be the previous frame, but we only want to look at the red points from the previous frame. So let's drop in a blast SOP, and I'll say at cd.r equals 1. Set this to points and delete non-selected. So now the previous frame will give us only the red points as we step ahead in our solver here. And we're actually not getting anything appearing yet inside our solver computation, and this could be because we decided on starting our solver at frame 95, but we haven't actually set it up to do so yet. So on the SOP solver here, let's set that start frame to 95 so we can get this thing evaluating. And I'm going to select the disintegration infection solver in my menu at the bottom of our interface here so that we can see what that evaluation looks like in our timeline. And let's display that solver and hide other objects in our scene once again. Okay, now you can see that we're only getting the red points as output from our solver at the moment. That's because when you're doing anything inside of a solver here, whatever flag you have the display set on is going to be the output of the solver on each frame. So we're not getting the distance from geometry as the output on each frame, even though it's the bottom of our network. Because the blast SOP is displayed here, the solver is only going to use this as the output every time this solver runs. So you always want to make sure that you drop in an output SOP so that no matter what you have the display flag set to, this output SOP is what the actual output of the solver is going to be. So this way we don't have to worry so much about having the display flag set to the correct thing. So now, even if the display is on the blast here, we exit out of our solver. Now you can see that the solver is still returning all of the grain points. So now back inside the solver here, I'll call this blast isolate infected, and we're getting the distance from geometry on all of our rest position points here. And if you check the spreadsheet on the distance from geometry and look at this output attribute dist here, we're actually just getting 0 for all of our grain points because it's looking for primitives to compare the distance to. And because we just have grain points coming in as the reference geometry for the distance lookup, this distance is just going to be 0 because it's not finding any primitives. So the reference group type will be points instead, and now we get some distances in our attribute spreadsheet, and we can use this to check the distance based on the growth speed and set the color accordingly. So now let's drop in a point wrangle, and I'm going to call this expand color and close our attribute spreadsheet. And first, let's set a distance threshold based on the grow speed attribute. So I'll say float dist threshold, and we're going to use a fit function on the grow speed. And because the grow speed is in a range from 0 to 1, we can use the fit 0, 1 function instead of the standard fit function, and then pass in our grow speed, and we'll vary this from a range. Let's try 0.5 to 1.5. So the white areas of that grow speed should expand 3 times faster than the black areas. And now let's compare the distance of each point to the red points from the previous frame and see if that distance is within the threshold to infect new points. So I'll say if at dist is less than dist threshold, then at CD is equal to the vector, which we'll create with the set function, which just initializes a vector value, and I'll set that equal to 1, 0, 0. So now if we display the expand color, you can see this has started to expand the red areas. And we could also give ourselves some additional information as well. Let's say perhaps you wanted to do something in the shader where we wanted the areas that haven't quite activated yet, but they're just adjacent to that. Maybe we want those to glow or emit some smoke or something like that. So we can set an additional color on the points that are about to activate next. So I'm going to copy this same if statement here, and then below that I'll type else and then paste that copy in there. And I'll say else if the distance threshold plus 1 is greater than the distance, then we're going to set this color equal to blue. And I don't think I actually used this for anything in the initial version of this project in general, but it is possibly some extra information that could be helpful to have. So now with these colors being set based on proximity to the previous frame's infected points, let's exit our solver here. And if we step through this, then you can see this expanding frame to frame. And let's run a flipbook to see what this looks like in real time. And finally, checking our flipbook, this infection rate looks pretty good, and we have some nice broken up leading edges here that look pretty interesting and organic. So these extra noises we applied on the growth speed are kind of nice to help kind of break up this leading edge and create some more interesting shapes there. And just to optimize things a little bit more, we can tell our solver to stop evaluating once everything is fully activated. And perhaps there's a more clever way to do this, but I'm just going to do it in a very manual way. So if we scroll through our activation here, we can see that everything is activated by, looks like, frame 155. So we can tell the solver to only evaluate from frame 95 through, we'll say 155 plus a few extra frames to really make sure things are fully active. So to clamp this solver to only evaluate within that range, let's drop in a time shift, attach that to our solver here, and I'm going to copy the start frame for the solver, copy that parameter, go to the time shift, and we'll turn on clamp to both, and I'll paste the relative reference into the start frame. So this is always based on whenever our solver starts, and I'll Control-Shift-Click on the end frame to get rid of that expression, or you can right click and delete channels to get rid of that. And I'm just going to manually set this to 160. And then just to be sure that things have fully activated, we can just do a quick check here. I'll drop in a blast and call this check inactive and connect that to our time shift. And in this group, I'll type @cd.r equals 1. The group type is points, and if we display that and middle mouse on it, you can see that all of the points are being deleted. So everything has been activated at this point. So now that we have this nice activation animating across the surface, we can apply the animation from the actual creatures onto these grain points before doing our final simulations.